matter can exhibit wave-like behavior. For example, a beam of electrons can be diffracted just like a beam of light or a water wave. Matter waves are a central part of the theory of quantum mechanics, being an example of wave-particle duality. The concept that matter behaves like a wave is also referred to as the de Broglie hypothesis, due to having been proposed by Louis de Broglie in 1924. Matter waves are often referred to as de Broglie waves. The de Broglie wavelength is the wavelength, lambda, associated with a massive particle and is related to its momentum, p, through the Planck constant. Wave-like behavior of matter was first experimentally demonstrated in the Davison-Germer experiment using electrons, and it has also been confirmed for other elementary particles, neutral atoms and even molecules. The wave-like behavior of matter is crucial to the modern theory of atomic structure and particle physics. Historical context. At the end of the 19th century, light was thought to consist of waves of electromagnetic fields which propagated according to Maxwell's equations, while matter was thought to consist of localized particles. In 1900, this division was exposed to doubt when investigating the theory of blackbody thermal radiation. Max Planck proposed that light is emitted in discrete quanta of energy. It was thoroughly challenged in 1905, extending Planck's investigation in several ways, including its connection with the photoelectric effect. Albert Einstein proposed that light is also propagated and absorbed in quanta. Light quanta are now called photons. These quanta would have an energy given by the Planck-Einstein relation, and a momentum where nu and lambda denote the frequency and wavelength of the light, see the speed of light, and h Planck's constant. In the modern convention, frequency is symbolized by F, as is done in the rest of this article. Einstein's postulate was confirmed experimentally by Robert Millikan and Arthur Compton over the next 2 decades. The de Broglie hypothesis. De Broglie, in his 1924 PhD thesis, proposed that just as light has both wave-like and particle-like properties, electrons also have wave-like properties. By rearranging the momentum equation stated in the above section, we find a relationship between the wavelength lambda associated with an electron and its momentum p through the Planck constant. The relationship is now known to hold for all types of matter. All matter exhibits properties of both particles and waves. In 1926, Erwin Schrödinger published an equation describing how a matter wave should evolve, the matter wave analog of Maxwell's equations, and used it to derive the energy spectrum of hydrogen. Experimental confirmation. Matter waves were first experimentally confirmed to occur in the Davison-Germer experiment for electrons, and the de Broglie hypothesis has been confirmed for other elementary particles. Furthermore, neutral atoms and even molecules have been shown to be wave-like. Electrons in 1927 at Bell Labs, Clinton Davison and Lester Germer fired slow-moving electrons at a crystalline nickel target. The angular dependence of the diffracted electron intensity was measured, and was determined to have the same diffraction pattern as those predicted by Bragg for X-rays. Before the acceptance of the de Broglie hypothesis, diffraction was a property that was thought to be only exhibited by waves. Therefore, the presence of any diffraction effects by matter demonstrated the waves-like nature of matter. When the de Broglie wavelength was inserted into the Bragg condition, the observed diffraction pattern was predicted, thereby experimentally confirming the de Broglie hypothesis for electrons. This was a pivotal result in the development of quantum mechanics. Just as the photoelectric effect demonstrated the particle nature of light, the Davison-Germer experiment showed the wave nature of matter, and completed the theory of wave-particle duality. For physicists, this idea was important because it meant that not only could any particle exhibit wave characteristics, but that one could use wave equations to describe phenomena in matter if one used the de Broglie wavelength. Neutral atoms. Experiments with Fresnel diffraction and an atomic mirror for specular reflection of neutral atoms confirm the application of the de Broglie hypothesis to atoms, i.e., the existence of atomic waves which undergo diffraction, interference and allow quantum reflection by the tails of the attractive potential. Advances in laser cooling have allowed cooling of neutral atoms down to nanokelvin temperatures. At these temperatures, the thermal de Broglie wavelengths come into the micrometer range. Using Bragg diffraction of atoms and a Ramsey interferometry technique, the de Broglie wavelength of cold sodium atoms was explicitly measured and found to be consistent with the temperature measured by a different method. This effect has been used to demonstrate atomic holography, and it may allow the construction of an atom probe imaging system with nanometer resolution. The description of these phenomena is based on the wave properties of neutral atoms, confirming the de Broglie hypothesis. The effect has also been used to explain the spatial version of the quantum Zeno effect, in which an otherwise unstable object may be stabilized by rapidly repeated observations. Molecules. Recent experiments even confirm the relations for molecules and even macromolecules that otherwise might be supposed too large to undergo quantum mechanical effects. In 1999, a research team in Vienna demonstrated diffraction for molecules as large as fullerenes. The researchers calculated a de Broglie wavelength of the most probable C60 velocity as 2.5 pm. More recent experiments prove the quantum nature of molecules with a mass up to 6,910 atomic mass units. De Broglie relations. The de Broglie equations relate the wavelength lambda to the momentum p, and frequency f to the total energy of a particle, where h is Planck's constant. The equations can also be written as where is the reduced Planck's constant, is the wave vector, and is the angular frequency. In each pair, the second equation is also referred to as the Planck-Einstein relation, since it was also proposed by Planck and Einstein. Special relativity. Using two formulas from special relativity, one for the relativistic momentum and one for the energy, allows the equations to be written as where denotes the particle's rest mass, its velocity, the Lorentz factor, and the speed of light in a vacuum. See below for details of the derivation of the de Broglie relations. Group velocity should not be confused with phase velocity. In the case of a non-dispersive medium, they happen to be equal, but otherwise they are not. Group velocity. Albert Einstein first explained the wave-particle duality of light in 1905. Louis de Broglie hypothesized that any particle should also exhibit such a duality. The velocity of a particle, he concluded, should always equal the group velocity of the corresponding wave. The magnitude of the group velocity is equal to the particle's speed. Both in relativistic and non-relativistic quantum physics, we can identify the group velocity of a particle's wave function with the particle velocity. Quantum mechanics has very accurately demonstrated this hypothesis, and the relation has been shown explicitly for particles as large as molecules. De Broglie deduced that if the duality equations already known for light were the same for any particle, then his hypothesis would hold. This means that where E is the total energy of the particle, P is its momentum, H is the reduced Planck constant. For a free non-relativistic particle, it follows that where m is the mass of the particle and v its velocity. Also in special relativity we find that where is the rest mass of the particle and is the speed of light in a vacuum. But, using that the phase velocity is, therefore where v is the velocity of the particle regardless of wave behavior. Phase velocity. In quantum mechanics, particles also behave as waves with complex phases. The phase velocity is equal to the product of the frequency multiplied by the wavelength. By the de Broglie hypothesis, we see that using relativistic relations for energy and momentum, we have where E is the total energy of the particle, P the momentum, the Lorentz factor, C the speed of light, and beta the speed as a fraction of c. The variable v can either be taken to be the speed of the particle or the group velocity of the corresponding matter wave. Since the particle speed for any particle that has mass the phase velocity of matter waves always exceeds c, i.e., and as we can see, it approaches c when the particle speed is in the relativistic range. The superluminal phase velocity does not violate special relativity, because phase propagation carries no energy. See the article on dispersion for details. For vectors using four vectors, the de Broglie relations form a single equation, which is frame-independent. Likewise, the relation between group particle velocity and phase velocity is given in frame-independent form by where for momentum for wave vector, for velocity interpretations. The physical reality underlying de Broglie waves is a subject of ongoing debate. Some theories treat either the particle or the wave aspect as its fundamental nature, seeking to explain the other as an emergent property. Some, such as the hidden variable theory, treat the wave and the particle as distinct entities. Yet others propose some intermediate entity that is neither quite wave nor quite particle but only appears as such when we measure one or the other property. The Copenhagen interpretation states that the nature of the underlying reality is unknowable and beyond the bounds of scientific inquiry. Schrödinger's quantum mechanical waves are conceptually different from ordinary physical waves such as water or sound. Ordinary physical waves are characterized by undulating real number displacements of dimension physical variables at each point of ordinary physical space at each instant of time. Schrödinger's waves are characterized by the undulating value of a dimensionless complex number at each point of an abstract multidimensional space, for example of configuration space. At the Fifth Solvay Conference in 1927, Max Born and Werner Heisenberg reported as follows at the same conference. Erwin Schrödinger reported likewise. In 1955, Heisenberg reiterated this. It is mentioned above that the displaced quantity of the Schrödinger wave has values that are dimensionless complex numbers. One may ask what is the physical meaning of those numbers. According to Heisenberg, rather than being of some ordinary physical quantity such as for example Maxwell's electric field intensity, or for example mass density, the Schrödinger wave packet's displaced quantity is probability amplitude. He wrote that instead of using the term wave packet, it is preferable to speak of a probability packet. The probability amplitude supports calculation of probability of location or momentum of discrete particles. Heisenberg recites Duan's account of particle diffraction by probabilistic quantal translation momentum transfer, which allows, for example in Young's two-slit experiment, each diffracted particle probabilistically to pass discretely through a particular slit. Thus one does not need necessarily think of the matter wave, as it were, as composed of smeared matter. These ideas may be expressed in ordinary language as follows. In the account of ordinary physical waves, a point refers to a position in ordinary physical space at an instant of time, at which there is specified of displacement of some physical quantity. But in the account of quantum mechanics, a point refers to a configuration of the system at an instant of time, every particle of the system being in a sense present in every point of configuration space. Each particle at such a point being located possibly at a different position in ordinary physical space. There is no explicit definite indication that, at an instant, this particle is here and that particle is there in some separate location in configuration space. This conceptual difference entails that, in contrast to de Broglie's pre-quantum mechanical wave description, the quantum mechanical probability packet description does not directly and explicitly express the Aristotelian idea, referred to by Newton, that causal efficacy propagates through ordinary space by contact, nor the Einsteinian idea that such propagation is no faster than light. In contrast, these ideas are so expressed in the classical wave account, through the Green's function, though it is inadequate for the observed quantal phenomena. The physical reasoning for this was first recognized by Einstein. De Broglie's phase wave and periodic phenomenon. De Broglie's thesis started from the hypothesis that to each portion of energy with a proper mass m0, one may associate a periodic phenomenon of the frequency nu0, such that one finds h nu0 equals m0 c2. The frequency nu0 is to be measured, of course, in the rest frame of the energy packet. This hypothesis is the basis of our theory. De Broglie followed his initial hypothesis of a periodic phenomenon, with frequency nu0, associated with the energy packet. He used the special theory of relativity to find, in the frame of the observer of the electron energy packet that is moving with velocity, that its frequency was apparently reduced to then using the same notation as above. The quantity is the velocity of what de Broglie called the phase wave. Its wavelength is an frequency. De Broglie reasoned that his hypothetical intrinsic particle periodic phenomenon is in phase with that phase wave. This was his basic matter-wave conception. He noted, as above, that, and the phase wave does not transfer energy. While the concept of waves being associated with matter is correct, de Broglie did not leap directly to the final understanding of quantum mechanics with no missteps. There are conceptual problems with the approach that de Broglie took in his thesis that he was not able to resolve, despite trying a number of different fundamental hypotheses in different papers published while working on, and shortly after publishing, his thesis. These difficulties were resolved by Erwin Schrödinger, who developed the wave mechanics approach, starting from a somewhat different basic hypothesis.